it would help if I actually put myself into the stream, Howdy, all. I'm Professor Parks, PhD, and I make content on astronomy, science skepticism, and mental health. So if you like these kinds of topics in sort of an informal format, or at least for now, then please consider sharing, subscribing, hitting the notifications, yada, yada, all that kind of good stuff. So here am I yet again, just shouting into the void. Today, the topic is astronomy as a science. And the reason for this is because I have been involved with talking to science skeptics for a number of years now. And one of the things, particularly from a certain group of science skeptics, that I hear a lot is that astronomy is not a science. And for some of them, there is a very large swath of what we would consider science to not be considered science. And I believe the defining line is really and ultimately is that unless you can actually physically manipulate it with your hands, then you have no idea what's going on. Essentially, fields like molecular biology, astronomy, astrophysics, cosmology, theoretical physics, all of these are not science because you cannot physically manipulate the object of interest. So, I thought, why not? Let me actually, and I've posted a couple of videos, and I think, yes, it was my conversation with an actual scientist. In the description of that video, there is a video that I made a long time ago, back when I was calling myself Rob World, entitled "What is Science?" And I'm going to link that episode in my description. Again, it goes over what basically the basics of the scientific method, what it means to be a science, what it means to be a pseudoscience, things of that nature. I'm hoping to be able to get friends of mine together at some point. PhD Tony, I Can Science That, AB Science. Sorry, dude, what is it? Iron, cobalt, nickel is just kind of hard to say. So AB Science, Professor Phil Bell, and others, and get them together on my channel and have a sort of forum talking about Bob the Science Guy, talking about what it is to use the scientific method. AB Science actually put out a fantastic video. I will also link that in the description. Where, howdy, Clive Wells. Clive, you are also welcome to join this forum, encouraged to join this forum. AB Science put out a video where he talks about the scientific method as a concept. And what he demonstrates or talks about is that the scientific method varies on how it's applied based on discipline. So, for example, a physicist, experimental physicist, has the potentiality to actually manipulate the object of interest within their own laboratory. Astronomer, often or not, more often than not, vastly more often than not, cannot do that. A psychologist can, in a way, manipulate the object of interest, which is typically human behavior, but they can't do it nearly as qualitatively or quantitatively as a physicist can. And so, depending on your field of study, depending on what branch of science you're doing, then you need to basically adapt. You have to, the core principles are still there, but how you implement them is variable. Now, if you hold on bear with me for one moment. I want to make sure that okay. I was just making sure that everything was groovy on the YouTube channel side, that my audio is good and all that kind of good stuff. Anyway, so I'm going to do there is, and I'm just going to minimize that. All right. So what I was talking about. But before I get into any and all of that, there are a couple things that I want to talk about. One of them, I'll start with a positive one, or the one that I don't think is, that I'm not as concerned about. And let me bring it up. Fudge. Hold on one second. As I should. No, I'm not going to say that. I'm going to say I should have had it up already, but no, fuck that. There it is. I'm going to do what I do. Oh, by the way, just kind of a heads up on my mental health. Yes, Clive, really. I'm surprised you haven't heard me say groovy in before, because it's one of my kind of, or used to be, I guess, one of my go-to little expressions, that and rock on. So yes, everything is groovy, man. Groovy. Anyway, so on my Discord, which I was going to put up a link showing the invitation to the Discord, but Discord now requires me to be a community in order for those invites to actually be infinite. So it's kind of defeats the purpose of having an invite code somewhere. So anyway, reach out to me, email me, or what have you. If you're interested in becoming part of my Discord and wanting an invite, please send it to me. Well, somebody managed to get an invite, and they told me about this particular channel. And let's do this. The channel is Maya Atkinson, and as you can see here, does a lot of live shows. Specifically this particular show called Bad Science Sunday. I only kind of gotten into this channel a little bit. I've only looked into it a bit, but in what I've seen, I really enjoy. It is a group of it's a panelist of various different people. Maya Atkinson is obviously the host, and they talk about various science skepticism, like global floods, hollow Earth, that sort of thing. So I find them to be the chemistry between the hosts to be excellent. So yeah, I definitely think that people should check this channel out. Please sub please sub to this channel. They're trying to get over. She's at 490 now. They would really love to get her over to 500 as much as possible, because then she can get the nice super chats. So yeah, if you haven't seen them or haven't checked out this channel, please do. And if you like what you see, please subscribe. Really, even if, so long as you don't hate what you see, please subscribe anyway. I mean, you just turn the notifications off, and it's as if it's not even there. So anyway, where was I going with this? Morning, Stephanie. 10 degrees in Texas. It is, hold on. Hey, Google, what's the temperature like right now?
In Fairfax, it's currently 31 degrees. Due to current wind conditions, it feels like it's 23.
Apparently it's 31, but wind chill makes it feel like they're on 23. Not exactly sure how they figured that out. Like, do they have random people all over the world, all over Fairfax outside being like, you know what? Feels like 25. No, dude, it's like 18. I don't know. I don't know how they figure that out. That's how I'm going to think that it does, that it happens, and you can't convince me otherwise. Luna, you're, as always, in the way. So what was I saying? Oh, yes. So yeah, please, Maya Atkinson. Here, I'll put it in the description. Paste. This hopefully is the link to her channel. It's 275 Kelvin. I see what you did there. Does that mean it's 2 degrees Celsius where you are? Do I have that in my head correctly? I can do unit conversion, sure. It's not like I teach it or anything. But from a more sobering perspective, some of you may know a content creator by the name of Triggered Limey. He is, I would consider him a friend. I'm certainly a subscriber to his channel. And he's had a rough go of it for a while. He has put out an announcement saying that he's done with YouTube, that he is essentially done. I am, due to my own experience, I am gun shy about welfare checks. I am gun shy about people assuming that I am in a worse state than I'm actually at. Yet, I can understand why, because in this situation, I am worried about Limey. I'm worried that he's going to do something rash, and I am concerned. And apparently, he's becoming more difficult to get a hold of. He's planning on selling off a good portion of his possessions. Like I said, I may be very paranoid about all this, but the language that he's been using, the giving away or the getting rid of possessions, it's sort of textbook. So what I would ask is if anyone out there who knows Limey or knows someone who knows Limey and can get a hold of him, I'd like him to know that we are concerned, because I'm not the only one. I've talked to a couple of other people from his Discord, and we are concerned for him. We know that he has gone through a whole lot of shit. He has health concerns, justifiable health concerns, and so we just want to let him know that we're here, and if he needs to reach out, please do. As people come to me all frequently, we're here if you want to talk. If you want to reach out and tell us what's going on, or not, just reach out to whatever. Let us know, and yeah. So I'm worried about you, dude. All right. Is she still with Dr. Tapioca Weasel? Yes, definitely Dr. Tapioca Weasel, because that is the gentleman who put me onto the channel in the first place. And he may be on the science forum. I don't know. I have offered him an invitation to come onto my show and get basically interviewed, maybe do one of those old coffee and sciences that I used to do, and just have a chat to get to know him and to introduce him to my audience, because he seems like a good dude. So yeah. Let's see here. I don't know Weasel. Or Ember, rather. I don't know Ember, or at least not. Can't place a name to that, or a face to that name, but I believe so. Yeah, they do Bad Science Sunday. Maybe we could do a double feature, because I used to do coffee and science on there. The other thing I want to say before I get back into the whole astronomy as a science thing is I just wanted to admit that I was a bit I took a shower. Hey, hair. Clean hair. I was a bit nervous about coming on. I almost didn't. Or postponed it, which means I wouldn't have done it. But I was like, nope. Good, bad, or ugly. I'm going to fucking get on and shout into the void. So, all right. Here, let's go. Where do I want to go with this? You know what? I don't have a paper handy, but I am going to try to download it. I know where it is. So much stuff. So scientific method, really superficially, is you see something, you ask, why is that something doing that something? And then you come up with an idea. Hey, I think it's doing that something because of this other thing. And then you devise a test, or well, essentially you devise a test of some form in order to see whether or not that other thing is responsible for the something that you observe something else doing. And yes, I'm going to keep doing that. You do that test, you analyze the results, and then you determine whether or not your results either confirm your hypotheses or falsify your hypotheses. Now, it's often shown as a binary option of yes, no. In practice, it very rarely is a yes, no situation. It's far more nuanced than that, because the things that you need to take into account are how well you did the experiment. Were there any problems with the experiment that you didn't foresee beforehand that caused some uncertainty? And even if you did the experiment very well and you are confident in your results, because science is so provisional, you have a responsible scientist is still never going to definitively say, yes, this is the best we can come up, or this is the solution. I have confirmed my hypothesis. This isn't the fucking Mythbusters. They're going to say something to the effect of, this is the best explanation. That's as strong as they're ever going to get, that a responsible scientist is ever going to get, is by saying that my results, my interpretation of my results, is the best explanation. Not the explanation, but the best explanation. Now, others, depending again on the quality of the data, depending on what they found, they will couch it in more, what's the word I'm looking for? Conservative terms. They will say, this is most likely what's going on. However, it could also be this, and this. I think for me, a good paper is one that you put forth your ideas, you put forth your data. For the most part, you have to show the results of your data. That's a given. You then make an interpretation of what that data means in relation to the question at hand. And you then basically try to justify why that is the case. But this, I think, what distinguishes great papers from good papers is that a great paper is going to provide alternate ideas about that interpretation. They're like, in the sense that this is our interpretation of the data. However, it is reasonable to assume that, or it is reasonable to say that this other explanation that people have thought of may also account for our observations. Now, the difference between a great paper and a phenomenal paper is a paper will actually look at those interpretations and then analyze them against their own data. They will basically say, all right, if we take this alternate, or this other interpretation B, how would that work with our data? And then they will give their honest assessment as to whether or not interpretation B is in fact a viable option for the data. All right. So ultimately you test the hypothesis, and on paper, if you Google it, if you go to Penn State or whatever and look up experimental physics or what have you, you'll often see this tree where it's hypothesis yes, hypothesis no. It's really, like I said, a continuum. But regardless, you get results and you say, hey, this is what we got. And then, as I like to stress to my students, perhaps the most important thing to do, the most important step within the scientific method, is publishing. You got to tell somebody what you did. Because if you don't, then what's the point? If you don't tell people what you have done, how you did it, then it's as if it was never done. It was as if the experiment that you did and what the results that you found, it never happened. Which is why I always couch my statements like Hipparchus. Hipparchus was the first to write down a catalog of stars. We don't know if anyone else did prior to Hipparchus, but if they wrote it down, then we don't have a surviving record of it. So publish. You always need to tell people what's going on because they need other resources, and this is where the scientific method becomes a loop. Is that your results, your interpretation, because it isn't really a binary yes or no, you have more questions. Because it isn't a settled thing, you have questions that will be spawned by those results. Those questions could be as mundane as, we need to do another experiment or a more precise experiment in order to test whether or not the explanation I have provided is in fact best, like get even more supporting data, or to say, all right, if we take this as our first stepping stone or the next stepping stone, what does this imply? What more can we do to advance this line of questioning, this field of study? One of the questions that is typically asked in my experience, the question that is typically asked in like PhD defenses or usually young scientists who are first starting out, putting out their results, is someone will inevitably ask, what's next? All right, if this is true, if this is the best explanation we have, then where do you go from there? The way I like to put it is, if you've got infinite money, if funding was not an issue, what is your next experiment or series of observations? So, you need to send your results to NASA? Yes, of course, yes. We need the overlords to say yes or no on it. Publishing is controlled by certain groups of people funded by big money, especially in medical field. This is why I don't know if you were around at the very beginning when I was talking about this idea of having a forum on my channel where we discuss scientific method in practice. And one of the things that I wanted to do is I want to be able to cover as many fields of study as possible. So obviously I've got astronomy covered. Phil Bell has physics. PhD Tony would have geophysics. Bob, the science guy, I don't know if he was a research doctor of any sort, but at least he is a medical doctor and has something informative to say about it. Oh, well, Clive, that's actually, I'll explain that in a second for those who don't know what archive is. So, because that could be an entire different panel discussion. In terms of how publishing is done, and I will revisit this at the end when I'm finishing off my the journey of this particular paper, because it was a fucking journey, is the review process. Now, the review process, the peer review process, I will be the first to admit it's not perfect. I will also be the first to admit that there are certain glaring problems with the peer review process to the point that it could actually bias results, potentially. I'm not saying that it does, but the potentiality is there, particularly in exoplanet science. From from talking to colleagues of mine, particularly a few years ago when exoplanet science was first coming out, there was an issue there that I don't know has been resolved at this point. I think it has, because exoplanet science has grown, but I am starting to get into the weeds. But Does Dr. Bob have a speciality? I don't know. I've never asked him, actually. Uh, stupid son. Anyway, which is the glowing ball of hydrogen, by the way, not a condensed matter of hydrogen, as some folks on the internet would like to claim it is. So in terms of, I will just say this, in terms of right now, in terms of peer review, the idea of big money being involved, no. Actually, that's one of the problems within the academia is, again, I can only speak to physics and astronomy because those are the only two fields of study that I am aware of, that I am most familiar with. But the problem becomes in that you are actually not paid to review papers. When you are asked to review a paper, and yes, it is a request, but it's one of those requests that, particularly if you're a young or mid-career scientist, you really don't say no, because that kind of boosts your rep, that kind of boosts your credibility, and then that has implications. So you don't really say no to these requests. I mean, you can, obviously, but they typically don't. The people typically don't, at least not all the requests they may get. You don't get paid for it. And so you have to take this piece of work, which is a piece of work. It is, if you want to do this right, if you're going to review a paper, it's time. There's a lot of time involved in doing so. And they don't get paid for it. So, yeah, I don't know. So if there is big money involved in astronomy and physics in terms of publishing, I don't know where it is. I can tell you that the only time that money comes into play is the journals themselves will charge for the privilege of publishing within their journals, or at least a good number of them. The APJ, Astrophysical Journal, Astronomy and Astrophysics, those two journals I know. Nature, you have to pay to have your stuff published, but that's what grants are for. So you could kind of kludgy your way into it. But NIMRAS, the monthly notice from the Royal Astronomical Society, is free, baby. Yeah, love them. So yeah. So like I said, I'll get back more into that later. You need peer review to get grants. You need peer-reviewed papers to get grants. Yes, that is true to a certain extent, but really the grants are weighed on the quality of the proposal that is done. The more papers that you can cite, the more work that you have done in that field is going to play a factor, because people don't want to, it's a human nature that you do not want to throw money at a unproven commodity, or there's a term there that I can't seem to find, but you're more prone to give money to someone that or have more confidence in is going to give you a return on your investment than someone who has just come onto the scene. Like I said, peer review grants, they ain't perfect, but I would certainly not go to the point that say that money slants, like heavily impedes or shapes research. Again, I don't know about the medical community. For physics and astronomy, money is not, there isn't some kind of big NASA saying, oh no, we don't like this idea, we ain't going to publish it. But it has its own problems. So anyway, you might get a voucher to get extra off prints of your next paper in that particular journal. Which particular journal? Nature? I have never published in Nature. A good friend of mine did, and he told me after that experience he would never do it again. Publishing in Nature apparently is a pain in the nuts. And he was not convinced as to whether or not it was worth it to go through that kind of rigorous. And the reason why it was a pain in the nuts is because it's rigorous. He had to jump through a lot of hoops before his results were accepted and taken seriously, more so than any other journal that he applied to, because they have Nature is a prestigious journal, so they have higher standards than anyone else, or most anybody else. All right, let's see. Trying to find this paper. Papers. There we go. Lambda Andy. All right, hold on. Where is the most? Wait a minute. I'm pretty sure I have a submission folder. Aha, I do. All right, sweet. What did I actually submit? So many drafts of this. Might have been quicker for me just to go to NASA ads and download the damn thing. Upload. See what's in there. Oh, okay. You know what? Budget. I'm going to do that. I have basically the reason why I'm saying that is because of the way that you submit. I don't have a PDF, or at least I'm not confident of which of these manuscript PDFs is actually the most current. So I am going to go to NASA Ads, which is where you can find a whole lot of papers. Why not? Let's do this. Of course, the sun is making it hard for me to see things. This is as arrogant or as vain as I'm ever going to get. So this is, so occasionally, I don't Google myself, but occasionally I have been known to, when was this published? I think this was 2020, let's say 2020, and I think it was 2021, but let me make sure. Okay. This was, yes, this one. There was a follow-up paper by a grad student of my former postdoc by the name of Arturo, who took my data, and his analysis of my data was way better than mine. He used some new techniques to analyze it, and so that was that paper. Let's see. Let's download it. Sure. Okay. Let's go to downloads. There we are. I do apologize because of the time of day. The sun is coming right into my monitor, and it's hard for me to see. So I think I can sit here, and everything would be groovy. Stop sharing. Present. Share screen. What is the title of this thing? There we go. Let's do that. Let's do this. All right. So let's run you. I'm not going to actually, I was going to say, let's run you through how a paper is put together. I'm actually not going to do that because that, I think, is losing the point or becomes a little bit of a tedious exercise. But I will just highlight certain things and try to highlight them and come back to how they relate to that scientific method that you're taught in high school or at the beginning of any, if you were like me, the beginning of any physical science class that you've ever had. So you have the abstract, which is probably, well, is the most read part of any paper at all. Basically, this is a summary of what you did and what you got. It is the elevator pitch of your paper. Then you follow with an introduction. And so what the introduction is, what it serves. Oh, okay. This is weird. There we go. What the introduction does is that, if you remember from when I talked about the scientific method, I talked about the first thing that needs to happen is you need to observe something. And then you need to ask the question, why is that something? Why is that something doing the something that you were observing, that you are seeing? So in this case, the observation that we are seeing is that for decades, we were looking at stars of a particular class, particular type of star, and those stars varied photometrically, meaning that they changed in brightness periodically with a certain pattern. Many stars do this. Many types of stars do this, but the pattern of periodicity, or the pattern at which how the star behaves, how the light diminishes, how it comes back, that can tell you about the mechanism, or that can inform you about the mechanism. For example, a Cepheid variable light curve, the way that the light diminishes and brightens with a Cepheid variable, which pulsates, is different in its appearance than, say, a eclipsing binary. Or in this case, what has been hypothesized is that these stars have star spots. These are like sunspots, only have vastly different characteristics. Effectively, this is a surface part of the surface feature that is, or part of the surface photosphere that is cooler than the rest of the photosphere or the surrounding photosphere because of the presence of a significant magnetic field. So best to write the introduction after you have written the rest of the paper. Yeah, I would say so. I would think so. I mean, obviously, as a researcher, you know what you are going to put into the introduction, at least in some part, but writing it, because of the way that and this again is kind of getting into the weeds, because of the way that scientific research goes, you might have an initial way of going, and then something happens, and you're like, no, I'm going to switch my focus and go in that direction. For those of you who are out there who are writing papers for the first time or what have you, write as you go. Write down everything, because taking notes and waiting to the last, or basically waiting till everything is said and done to just sit down and write a paper, in my opinion, sucks. Looking at that blank screen and trying to figure out what I'm supposed to put there, I would have, if I were to do this again, I would be writing as I went, at least in kind of a rough sort of draft-ish sort of way. That way I'm not staring at a blank piece of paper when I am doing, when I'm done, when I want to submit my results. So the observation is the varying of light over time. The hypothesis is that the reason why it varies is because these colder spots, which don't put out as much light, they come into your field of view. The overall amount of light that you see from the visible part of the sun or star is lower. And then as the star rotates, the spot gets carried to the backside or far side of the star. And this star side presumably doesn't have as many spots or no spots and is brighter. And then as the star rotates again, it brings the spot back into position or back into your line of sight. And so the light goes up and down periodically based on the rotation period of the star. This is an interesting astrophysical question for a number of different reasons. One, it can give you the rotation of the star. It can give you how fast these stars are rotating, which talks about how these stars formed and how and it comes back to the magnetic field. If the star is slowly rotating, then there are implications as to how that magnetic field was used to slow its initial rotation. Speaking of the magnetic field, depends on what you're interested in, but star spots. Right now, we have the most robust data set we have to explain the creation and behavior of a stellar magnetic field is for our sun. And so that's a data point of 1. All the other stars are way far away. So trying to get more data to support our ideas of how magnetic fields are generated, you have to look to these kinds of stars in order to get any kind of data in order to expand the theory, to see whether or not, for example, the sun's magnetic field generator is markedly different than anyone else's. And in this case, for these particular stars, it is hypothesized that in order to produce the curve that you see, the light curve that you see, these star spots have to be abnormal, these star spots have to be very unlike the spots that we see on the sun. They are huge, they are limited in number, and they are long lasting. These are spots that last for months in typical cases, whereas the sun spots typically last for weeks rather than months. There are other peculiarities that need to be studied that are the differences between the two, and these point directly to a different formation or a different mechanism by which magnetic fields are generated in stars, and that then leads into a whole host of other astrophysical concerns. Howdy, Judy. Judy, do you know what Dr. Bob's medical specialty is? Stephanie was asking. So, introduction, scientific method. What the introduction does is it does just what I just talked about. It identifies the problem, or it identifies, typically you identify the original source of the observations. You then go into a discussion about a brief history of how those observations were interpreted, what techniques were used, and then finally you end the introduction with, this is how I'm going to look at this problem, and this is why my technique is going to give us better information than previous studies. This is why I'm good and they are crap. No, kidding. Internal medicine. I was thinking that he was a GP as well, but I honestly have never asked him. Howdy, Fred. So that's the introduction. That is the first part of the scientific method, identifying a problem and hypothesizing what's going on. My hypothesis in this point is, in this particular paper, is that the variability that we are seeing is in fact due to monolithic spots that rotate, that are long lasting and rotate over many cycles. That's basically my starting hypothesis is that I am looking to confirm what everyone else has done, or I am looking to confirm what the prevailing idea is. However, I'm using a technique that will potentially allow me to falsify that idea, to see whether or not these spots are in fact long lasting, or they are in fact not monolithic. They are instead a smaller chunk of spots rather than one big honking one. And the technique that I'm going to use is called interferometric interferometry. I'm not going to get into the weeds of that. Interferometric interferometry is a complicated observing technique, but I will do my best to kind of walk you through it. So the next section of the paper is observations and data reduction. This section This section talks about basically, this is our experimental setup. These are the bits of data that we have collected, and this talks about what data was collected and how it was collected. I took first, this first section, 2.1, is really just describing the bulk characteristics of the star. And, we talk about how, what is its mass, or what is, what did I put in here? Its periodicity, which is around 54 days. It seems to have an activity cycle of about 11 years. The mass ranges anywhere between 0.65 to 0.85 times the sun's mass. So really just kind of going over what other people have done in terms of its, in terms of what we're looking at. It provides a sort of set of initial conditions that can be tested. Then I go over the interferometric observation. So just very briefly, what an interferometric observation is instead of using a single telescope to look at your object, you use many telescopes to look at that same object simultaneously. Radio astronomy does this technique as well, but they are dirty, dirty cheaters, and they can basically look at it with one telescope, wait for the Earth to rotate, look at it with another telescope, and play with it later. For optical and near infrared observations, interferometry, you have to do it in real time. You cannot save the photons and then combine them with other saved photons later on down the road. So I am using, in this case, I am using 6 telescopes looking at the star Lambda Andromeda simultaneously. And I am combining the light from various parts of, I'm combining the light from various different telescopes in order to simulate, and this is the important bit. Through this process, you can simulate the angular resolution. And Gary, if you're listening, this is informative to you. You can simulate the angular resolution that you would get of a single telescope that was the size of your telescope array. Physics tells us that the amount of fine detail that you can see is limited by the size of your collecting instrument, the size of your telescope, the aperture of your telescope. Bigger is better, baby. And so even with the biggest telescopes on the Earth, even with Hubble, this was before JWST, even with Hubble, there was only one other star that could be resolved, that could be seen as a disk rather than as a point of light, and that was Betelgeuse. Betelgeuse? Guess not. Oh, I guess it's the other way of saying it. Anyway, Betelgeuse was able to be partially resolved by Hubble. It was actually seen to have a spot on it. It's actually pretty interesting. Anyway, no other stars could be. No other stars could be resolved. Now, prior to my investigation, using this technique, others have actually resolved the surface of, had resolved stars into disks or disc-like shapes. Stars like Altair are actually kind of rugby shaped because of their such high rotation rates. But that resolution could only tell you the shape of the star. This technique, the technique that I developed, can tell you what is going on the surface. Now, using this technique, my hope was, and I have thus done so, and it has been shown that I did, I was able to actually see finer detail on the surface so that I could see whether or not spots existed and where those spots occurred. So the interferometric observations, I used the Char array on Mount Wilson. Ultimately, I took 1 meter telescopes and combined them so that I was using a telescope that simulated the angular resolution of one that was 331 meters in size. To give you an idea, the biggest single telescope on the Earth is actually the biggest single biggest telescope is 10 meters. So my telescope was 30 times the size of that, which allowed us. Then I give it an observation log. These are my data points, or these are the observations that I made. These are the stars that I use to calibrate my data. Very important, basically, because if you don't calibrate, then you really have no confidence as to whether or not your data is saying what it is. And this is also very important, it is, in my opinion, dull as fuck. It's one of the worst parts of writing a paper. Other people get a large kick out of this, but I ain't one of them. It's measurement errors. You have to go into a discussion about how your data was processed and how that through that process errors came into being. There is no experiment ever that doesn't have errors. Instrument error is a thing. You cannot get rid of instrument error. You can narrow it down. You can make instruments so precise the error shrinks to ungodly sizes, but you can never get rid of that instrument error. And then through the process of calibrating your data, you can also introduce other forms of error. Photometrically, you can introduce what is known as dark current, which is an error due to photons that don't come from the star, but come from the camera itself, and other such things. So now you have described how you got the observations. You have described how you have analyzed those observations, and now I have discussed what errors have propped up in that analysis, and I give basically, this is where I state what my error bars are. So if someone else wanted to come by and look at this paper and say, all right, why should I believe your results? Well, they can see how far away from how big my error bars are, because the larger your error, the less confident you are. And they can look at those error bars and say, okay, well, this tells me that you are confidently describing something, but how do I trust those error bars? Well, this is how, at least in my way. Hopefully when they look at this, they will be convinced that the error bars that I am showing are real, are factual, or at least overestimations rather than underestimations. Then we'll go into identification and removal of poor data. I know that might sound scary, but yes, you can in fact remove errant data points because, again, measuring instruments are not perfect. They can hiccup, particularly electronic instruments. So there are accepted ways of clipping your data, of getting rid of data that you know that you have a high confidence of that is not real, is not actually showing you the proper behavior that's happening from the source. Now, you can't just do that. You have to, if you do that, you have to describe and justify how and why you did it. And again, someone who is interested in this, someone who wants to have confidence in your ability to what you're saying, they can look at this and they can be like, oh yeah, this makes sense. Or they can look at this and say, this is complete bullshit. Because this is complete bullshit, I am going to ignore everything that you've written. It happens. That is why it's there. That is the honesty that scientists hope to achieve or hope to ascribe to, is that they will honestly show how the sausage is made. The other thing here, 37 and Lambda Andromeda has a companion, a very, very small, very, very faint companion that would affect my observations. So I had to go through an analysis to illustrate just that given the precision of my measurements, 37 and I'm sorry, Dana. I'm cart before the horse. 37 and is a calibrated source. It's a binary, but I had to go through to show that its binarity. It's the fact that the stars are, there are two stars there instead of one, why that would not affect the calibration. Then I partnered with a collaborator, Dr. Greg Henry from the University of Tennessee. This is also another way, or another great example of how science is done. Science is collaborative. If I were to go back, okay. I don't know why that. This section up here, those are all the people involved. I wrote this. I was the principal investigator. I led the experiment, or led the series of observations. I did the analysis, but I didn't do it in vacuum. I asked people. I asked people for help. And some people, like Greg Henry, they actually contribute data to this project. This is how science is done. Science is not done by, generally speaking, science is not done by a single investigator. It is a group collaborative effort. So you got to have people skills to some extent or another in order for that to happen. Where'd it go? Why is it doing this now? 37. And so from Dr. Henry, I got some photometric observations, which is a different type of observations that is completely different than interferometric observations. Why, you might ask, I want to do this? Because I'm going to use the photometric data to test whether or not my interferometric data makes sense. Yes, I was thinking the same thing when I said that. Sirius is the only binary star. So this is yet another important step within the scientific method, is that it needs to be verifiable. It needs to be sort of falsifiable. Now, there are ways of doing it. Again, that's not really a monolithic thing. For a single experiment, what that means is that what you are attempting to do, the best types of experiments, are experiments that are trying to arrive at the same conclusion or test the same thing, but in two separately different ways. Therefore, you know that if you get a result from one type of observation and you get a result from the other type of observation and they match, then you have more confidence to say that, aha, this is what's going on, or this is you have more confidence, not to say that this is what's going on, but you have more confidence to say that it's the best behavior or best explanation. The two, if they don't match up, then you know you've got a problem, and you've got to rethink your experimental design, and then you have to go back. You have to go up the chain. You have to redefine or redesign your experimental design, or in this case, observational strategy, and then you have to do it over again. So I use this as a checking system to see whether or not my new snazzy method would give any kind of results that I can, buy and trust. And I show what those observations are. And so Dr. Henry has made a career of looking at these types of stars with his telescopes at the University of Tennessee, and has just massive amounts of data. Here I'm looking at data that is, what is this? Here is only a subsection. This data was taken contemporaneously with my observations, because I wanted to compare apples to apples. I have this photometric data that I want to compare with my interferometric data. Well, I can't very well take photometric data from 2 years ago and justifiably say that, yeah, my interferometric data, if they match, then they match. Because who knows what would happen from 2 years to now. Even though this star may have been behaving the same way for 50 years, you still need to take contemporaneous you have to take observations that are close in the same time frame as your observations. They're not simultaneous. Sadly, I could not get simultaneous observation because the weather conditions in California and the weather conditions in Tennessee on average during this time were not conducive. There was no way, basically it was cloudy in Tennessee when it was clear in California on average. So there was no way for me to get, and also I took data on certain days that he didn't take data. So yeah, they're close, but they're not an absolute match. Thank you, Clive. And I have a website. I'm going to promote it now. I have a website, Professor Parks, profparks.net. It's still being under construction, but one of the things that I'm going to do is, of course, I'm going to brag about myself, and I'm going to put all of my publications on there so that people can check them out. So yeah. Now, and this is the part that's probably the most contentious with certain folks within the science skeptic community. As I was saying at the very beginning of the stream, astronomy cannot physically manipulate the object of interest. And for the love that is all that is holy, if you think about the R word, don't tell me about it. Don't put it in my comment section. Don't tell me about it right now. Your understanding of the reification fallacy is wrong. If you use that term, you're wrong. Just putting that out there right now. So the way that astronomy works, particularly in this sort of analysis, is that we have to come up with, I have to better define my hypothesis. I have to do so in a quantitative way. I have to basically come up with a way of saying that if there is X spot of X size of X temperature on the star, then that is going to give me specific numbers of the data that I should have collected. I've created a model. Don't say the R word. Don't even think about the R word. So I've created a model. And again, here, I have done so two different ways, which I'll get into. Well, I've done so two different ways. Which is, I have created what some might derisively call a cartoon model, and then I have used a particular type of interferometric. Stephanie, don't even bother looking into it. No, please. If you want to look into it, it's fine. But I've created a cartoon model, and then I've created I've used what is known as image reconstruction, which is a completely separate way of doing this, but in principle, the process is the same. All right. So this section, 3.3 is the star spot analysis. And so in 3.1, I describe what my star spot, my spotted model is. Now, I'm going to back up a moment because there are certain folks out there who are like, the control variables. Okay. Sorry. I had a bad interaction with one of these folks. And so I'm going to keep it more polite. So a lot of people talk about this thing called control variables, independent variables, and dependent variables, IV, DV, CV. Astronomers, professional astronomers, we don't refer to that. We don't think of it as that way. We don't use those words, but we do use those variables, which is why when I first came into this, I honestly didn't even know what the definition of an independent and dependent variable was. And QE, you can snip the shit out of that if you want, because I didn't think of these things in those terms. I didn't think of IV, DV. What I thought about was, what is my data? And what can I manipulate within my model in order to match up the results? So my model has a number of different switches, has a number of different parameters. The size of the star, the limb darkening coefficient of the star. So those two have nothing to do with spots. Those have to do with the physical size of, or the physical properties of the star as a whole. Now for the spots. Where is it in longitude? Where is it in latitude? How cold is it? And how big is it? So I have six variables that I can manipulate, that I can, whatever you want to call it. I don't know if that's the IV or the DV, but those are the switches that I can throw. Those are the things that I can play around with in order to get the back end. Now, again, my interferometric technique, that gives me two pieces of data called the visibility and the closure phase. Not going to get into that because that requires an understanding of Fourier analysis. But just simply put, the visibility is the brightness of the object you're looking at, how that brightness is distributed. Well, actually, just the brightness of that object. And closure phase is, you can think of it very roughly as the contrast between different parts of brightness within that picture. So I get these two pieces of information. This is what I observe. I observe visibilities and closure phases. My model that I've created I create an image, a cartoon image, granted, it's not very sophisticated, because this is also a lesson. You do not want to create a model that has 5,000 switches, because, as a friend of mine very cleverly showed, if you have a lot of switches, you can literally show that the difference in a variability of a light curve can be approximated by Santa Claus going across that star with his reindeer. That's if you have a lot of switches. That is the lesson that we learn, is that you want to get as few parameters in your model as possible, or at least be able to figure out a way to hold fixed as many parameters as possible, because then you can't fit Santa Claus to it. Then you have, again, more confidence as to how you are, more confidence that your representation of the star is, in fact, the actual view of the star. So I got 6 parameters. Through my experimental process, I realized that if I allowed all 6 to run wild, I never got a result that was that converged. Because if I didn't already state this cartoon that I created, I can extract visibility and closure phases from if I were to observe that object with my instruments, with the char array. So if I took the model that I created, I put it up in the sky at the same time, in the same location as the star, as Lambda Andromeda at that time, this is what I would have seen in visibility and closure phase. You can then compare that modeled visibility and closure phase with the observed visibility and closure phase, and I hope it's not too irrational to think so. If the two are the same or within error, then you now have confidence that what your model is saying is actually what is there. Well, I did this. I ran through, I let all 6 go because I said, hey, what the fuck? Just let's have fun. Let's roll the dice. Yeah, it didn't work. There's a lot of didn't work in this process. So I was like, all right, this is too many to vary. Like the computer or the code has no idea where to go. So I was like, all right, well, let's take this a little bit more basic. Let's figure out what the star itself looks like before we deal with the surface of the star. So I basically ran an analysis where I said, all right, the star has no spots. The star has no spots at all. It's this size, it has this limb darkening. And then I ran it and I came up with results later on. And I found the best fit. I actually got convergence, what we call convergence, where the variables, the closure phase and the variability of visibility of the observations and the model matched up pretty well. Actually, this tells you something. I am a Santa denier, yes. This actually tells you something, because this is if you remember the hypothesis is that these stars are spotted. They have spots. So if I had created a model that didn't have spots and it fit the data very, very well, then I can immediately say, nope, there are no spots here. I'm not seeing any spots. So, oops. But I did. The data suggested that the best fit of a non-spotted star wasn't great, but it was enough for me to constrain what the size of the star actually is and what the limb darkening coefficient actually was. I then compared that to previous observations with using different techniques, and lo and behold, they matched. They were within the error. So I had confidence that those two things I had figured out, and I nailed them to the wall. Again, I have to be I have to be honest. I have to point out that with this technique, there is what we call a degeneracy between size and limb darkening, meaning that the quality of your fit can be the same if you make one go up and one go down by a certain fraction. So essentially, you can have the same. You can have slight differences in both parameters, and you'll get the same quality of fit. That doesn't mean that the results should be thrown out. That just means that it informs what the error bars are, and it lets you know that if there is evidence somewhere down the line that I drastically had no idea how the limb darkening should be portrayed as, then my results are definitely in question. The size is way bigger than I originally determined it to be. So that's also why this paper, why it has to be in the paper, is because when somebody comes back and looks at this result and says, all right, there is this correlation between limb darkening and size. But this recent paper says that the limb darkening, there is no limb darkening on the star, and they know it very, very well. That then informs them that the best that that can be interpreted from this paper is that my size, they have to go with the largest size that I quote. And it calls into question, it lowers the confidence of the results of this paper. Again, that's how science works. That's how modern science works, is that with new information, we are checking and balancing what we know and what we present. Image reconstruction, Squeeze. This is a computer program that was coded by my postdoc advisor. Really not going to get into the nuts and bolts of that, but essentially it moves around the brightness of a star. You give it basically a starting point. Again, I started off with a uniformly bright disk of the size of a certain size, and I allowed the brightness to go wherever it wanted to. There were certain constraints so that the brightness couldn't go negative, for example. It goes wherever it wants to. And then again, the code will produce visibilities and closure phases with each iteration, with each distribution of brightness. It produces a visibility and a closure phase. It then compares that to the observation, says the fit is this. Next iteration, next model data, next comparison, next quality of fit. If this quality of fit is better, then it goes in the direction that it was going. If the original quality of fit was better, then it takes another tack. Hopefully that makes sense. All right, so I do this, and now I talk about the results. I have a number of data sets taken from in both 2010 and 2011, and I talk about the properties that I have arrived at, or the properties of the star that I have determined through the analysis of this data. This is technical stuff. This is the basically the coverage in the UV plane. This is the closure phase data. Right off the bat, if this thing were not spotted, the data would be at 0, 180, or negative 180. There would be no data points between the two. So just looking at the data, I knew that this was not a unspotted surface. Well, I knew looking at the data that this was not a uniform disk. And so here we go. These are the results, the physical or the visual representations of the star. Really what I want you to do is I want you to look at the top two. This bottom one is essentially it goes into error confidence. So trying to identify image artifacts, particularly in this middle column. For example, this white dot that looks like a cool dude with glasses and a shiny nose. Is this shiny nose real? Well, based on this observation or this analysis, no, it's not. This shiny dot or this bright patch is actually due to the method that was used to create the image, basically an image artifact. So I need to have a robust way of identifying which of these features in these stars I could have confidence to say that they were real, and I could have confidence to say more specifically, okay, for example, you kind of see these two dark eyes in the comparison image, but they're not as dark as what you would expect in the actual image. So what that tells me is that those spots are real. It's just they are not as dark as in reality, or they are probably not as dark as they are depicted effectively. This is my cartoony model. Isn't it lovely? I am very proud of this because I am not a coder, and figuring out how to actually, and yes, this is embarrassing to say, figuring out how to actually code a 3D environment or a 3D surface using IDL back then, not easy for me. Not easy for me at all, particularly with the idea of putting a spot on it and actually having it foreshortened properly, meaning that one of the baked into assumptions of this model, of my model, is that the spot is circular. That's an assumption and may not be a good one, but it's the best that I can do. And if you put a spot down, then obviously if it's circular, but if you're looking at it, if the spot is over to the side, then you're looking at it as it is foreshortened, and it's no longer, it doesn't appear circular to you. Still circular, but to you, it looks oblong. And so what we see here is just visually, I have quantitative analysis to back up this claim, but you can see there is a correlation between these two independent methods, that there's a large shallow spot here. There are a couple of shallow spots here. Some darker spots are coming in, and so forth. And through this analysis, this is the reduced chi-squared. I was using a reduced chi-squared method for this. The most recent interpretation of this data actually used Bayesian statistics, which is a far better way of going about it. But this is the reduced chi-squared. The lower the number, the better the fit. A a value of 1 is basically a perfect fit. And so what we can see is that as I introduce spots, the reduced chi-squared got changed. Another thing is, again, I could throw as many switches as I could. I could have lots of switches because my model was such that I could create any number of spots on the surface. None, 1, 50, any number of spots that I wanted. Each spot has 4 switches. Each spot has its own longitude, latitude, color, or depth, or temperature, and size. If I add another spot, I'm adding another 4 parameters. If I'm adding another spot, I'm adding no, I don't have a third arm. I'm adding, you see where I'm going with this. And so I made the decision that given the resolution of my instrument, that it made no sense to add anything more than 4 spots. So my process was I will add spots until the chi-squared gets worse, or I get to a 3-spot maximum. Because again, if I put too many spots in, then I'm starting to model Santa, and that's not what I want. So here's what we see, and so you've got this core. What looks to me, and again, I have quantitative analysis to back this up, or to lend credence to this claim, is that these 2 independent means of determining what the surface of the star looks like agree. Now, I will try to convince you, and again, you can read the paper. When I couch this, I am using very qualitative language in that this could be, this looks like, that sort of thing. I'm not saying it is, but I try to convince you in some way, but I still leave it open to the idea that I could be wrong, particularly in the specifics. You have this spot, you have that spot. You come over here a week later, you have this thing over here. You kind of have something maybe over here. You have this little spot over here. You kind of have maybe something over here. A week later, you see this. What my contention is this big spot has moved to the limb. This spot is now that spot, and these spots were behind it, were not seen in this earlier epoch. What I am seeing is the literal rotation of the star. The star is rotating within my observations, and I am seeing the star in different snapshots of the star in different times, and I am seeing the stars move across that surface, which would be why we believe the photometric observations do what they do. Is why the photometry dips and rises is because of the movement of these spots. And then you can go over here. These 2 spots, these 2 spots. This spot, that one. The 4th spot may not be there. And then, again, you can kind of see it here and so forth and so on. So I'm like, whoops. Hey. I got somethings, maybe possibly. If you're still here, Norm, thanks for watching. Hope you can catch the rest of this. Stephanie, could you be seeing the frequency of the star? Can you be more specific as to what you mean by that? And then here are the star spot properties. I go through a certain analysis to, again, to lend credence to my interpretation of what I am seeing is what I just told you is what I'm seeing. Here, what I am showing is that this is the photometric observations done by Dr. Henry. These stars, these red stars, are the amount of photometry you would expect to see given the star, which appears as I've shown it. So, yep. Where did you go? There he is. Whoops. So if you were to take all of this, if you were to take the amount of light coming off of this star, you were to take the amount of light coming off of this star, or this image of a star, and so forth and so on, you can create a synthetic, or a modeled light curve. And I don't know why it's doing this. And that's what I've done here. And for 5 of the 6 epochs, and there are no error bars here. Well, for one thing, the photometric error, photometric error on the photometry is so small as to not be plottable on this. So the errors for the photometry are very small. So those observations are very precise. The reason why I don't have error bars on the red stars is because this is a very crude way of doing this. And I did not have a way of, I could not figure out a way to estimate what my error bars would be. So I said, I'm not even going to show them. But in the text, I explained that the reason why there are no error bars is because I did not know of a way to honestly represent them. Yes, this spot, no idea what's going on here. And again, I mentioned that. I'm like, 5 of the 6 match very well, seem to match very well. That 6th one, no idea. I make some comments as to why that didn't work out. Who knows? I went a little bit further. I then said, all right, if these are the spots, because I know their positions, let me see if they will match latitudes. Because essentially what we don't expect the spot to move in latitude over a rotation. So it basically should be a line across the star, a straight line across the star. And all of the spots, those lines should be parallel. Well, 2 of the spots near the mid-latitudes, or near the equator, kind of near the equator, or at least lower down in atmosphere, or lower down elevation, yeah, looks good. These 2, not so much, exactly. But this, we get into something known as small number statistics, is that, I only have a few data points here. So again, in the paper, I approach this and basically say, here is what happened. I did this. Here's what happened. This is what, 2 of the spots seem to be consistent with my conclusion. 2 of them, not so much. Take it however you want. But I say it's provocative, ain't it? I then talk about that do the spots change over time? Because that's something that we want to know. And again, the current the idea before this was that the spots do not change in temperature or size appreciably over a rotation. And they kind of don't. Some of them kind of do, or they kind of don't. On top of that, I also computed what the period of the star would be if you looked at the motion of one particular spot. Here again, not great. Photometrically, this thing has a rotation period of roughly 54 days. My rotation rate, if you averaged all these together, yeah, it's consistent with 54, but the error bars are huge. It's consistent. Then I get into the 2011 data. I get a lot more, I got a lot more data. I actually used a different technique. With 2010, I actually used 4 telescopes in the first half of the night, and then 4 different telescopes in the second half of the night. In 2011, I was able to convince folks that I could do better if I was greedy and got my grubby little hands on all 6 and used them at the same time. During this time, I was not the most popular person because I was using all 6 telescopes and nobody else could observe at the same time that I was. Ha ha, nanny nanny boo boo. So I did the same analysis in 2011. Unfortunately, the data was not as good. The quality of the data was not as good. And so I did get results. They did show some form of agreement, but the agreement here is not nearly as good as in 2010. So what this tells me is that either the weather, and I think it was weather, either the weather at this time was more variable, and so the quality of the data was crappier. I probably should have looked at the error bars and not, but whatever. Or something about using 6 telescopes as opposed to a 4 and 4 combination actually is worse. Even though you get more data, it's actually it makes the data analysis more convoluted. I don't know. Again, mention that in the paper. Do the same thing. Photometric analysis. Here I'm basically only seeing 2 spots. And again, for those 2 spots, yeah, the axial tilt of the star seems to match or is consistent within a certain area. I then summarize my results and basically take everything that I've just told you over the past hour and a half and condense it down to a hopefully concise and hopefully clear explanation of everything that I've got. And in this, I talk about, see, here it is. There is evidence to suggest that star spots imaged in one epoch are, again, imaged in subsequent epochs. There is evidence to suggest. I don't say that there is. I don't say that star spots seen in one epoch are the same spot seen in another. I say that there is evidence to support that conclusion, not that it is actually factually accurate, or that is the truth of the matter. And yeah, and then I calculate those results, and I again compare them to previous results. They're consistent. In some cases, they're better. Well, actually, in almost all cases, the error bars are better. For me, go me. And yeah, so at the end of the day, and then for giggles, because I had to put up with this, so my referee had to put up with this, and my author or readers have to put up with this, is that 2010 was not the first time I observed this star using interferometry observations. First time was actually in 2008, and then again in 2009. They didn't go well. The data was so sparse that I could not conclusively say anything about what was going on. The data did not match in any way, shape, or form. And so it forced me to evolve my process. It forced me to evolve or rethink how my observational strategy. Here, I was only using 4 telescopes. That's it, just 4 over the course of a night. And I don't think I was doing it over the course of the entire night. Maybe it was, but I was only using 4 telescopes. So when I got these results, I sat back and had a rethink. I was like, this isn't. I had confidence that I could do it. I had confidence that the instrument was capable of finding the data that I wanted, of being able to resolve these spots. I just needed to figure out a technique that could actually do it. And so that is where I came up with my 4 and 4 strategy. And then that's when I came up with 6, because, and this is the sort of political part of it, the telescopes, everyone wants to use, a lot of people wanted to use them. So the reason why I initially went with 4 is because people were like, dude, you can't have all 6 for an unproven idea. You have to give someone else a turn at the instrument to collect data for themselves. You can't hog the thing. So I did that. I was able to show that doesn't work, but there is indication in these closure phases that there is something there, and that I then did some analysis and was able to show that if I had more data, it would be mo better. And so they gave me the 4 and 4. opportunity. Now I'm using all 6 over the entire night, but I'm not using all 6 at any one particular moment. That's when I got the 2010 data. I was then able to convince them, hey, this is what I got. Imagine what I could get with 6 at the same time, which is why I was able to get my observing run approved with 6 telescopes. Sadly, because again, it's been a while. Obviously, 2011, it's been over a decade. I don't quite remember why the 2011 data was not as compelling. And yeah, that is my paper entitled Interferometric Imaging of Lambda Andromeda, Evidence of Star Spots in Rotation. Again, evidence, not star spots in rotation, evidence of star spots in rotation. Actually, my PhD advisor cautioned me on ever saying anything definitive. His approach is actually not to include interpretation of the data. His approach is to take the data, publish the data, and say what the values are. Like, this is the mass of this star, this is the rotation, or this is the radius of the star, or what have you. These are the properties of the thing I looked at, and then leave it at that. Leave the interpretation up to the reader. I was young, trying to make my bones, and so I was like, no, I need to. He's like, all right, if you're going to make any kind of claims, you need to really make them soft. Later, I was vindicated in a way. Arturo, the second paper in the series, Arturo used the same data but more sophisticated analysis methods. I was right, baby. Yeah. Not as he got a better map, but my map is consistent with him. So anyway, enough of my bragging on myself. Now, I will, and again, I've been going on for about an hour and a half now about something that probably very few people are actually interested in. But I want to finish this off by saying, with the scientific method, just kind of recapping this, is that with this particular paper, this is astronomy. With this particular paper, I noticed a behavior in a certain type of star, which had been attributed to a certain phenomenon, star spots. I then devised an observational strategy to use a new technique, new piece of equipment, to measure those stars. And then I devised an experiment through modeling to test that hypothesis. I then analyzed that data, and then I gave my conclusions as to whether or not my hypothesis was validated or not. I want to stress that this is not an on or off switch. This is not a binary option. There is no yes and no. There is a continuum. For me, the continuum was, okay, I have evidence that before we were looking at it, we were saying, all right, there is maybe 1 or 2 monolithic spots on these stars, on Lambda Andromeda specifically. What I'm showing is that I have evidence to suggest that those monolithic spots are not nearly as monolithic as we think they are. They are, in fact, broken up into smaller, more not circular, and they are broken up into a larger number of smaller spots that are not evenly distributed. So, did I confirm the hypothesis? In some ways, yes. In some ways, no. I did support this experiment supported the idea that yes, in fact, there are spots on these stars. They are physical star spots on these stars that behave like sunspots. Were the spots monolithic? No, not from what I'm showing. But again, all of that needs to be taken into consideration that this is not the definitive answer. This is simply what I have found to be the best explanation possible. I then published it, or I then sent it to a publisher. This was in AppJ, I think. Yeah. I sent it to AppJ. Somebody reviewed it. Somebody really didn't like certain things that I did in the initial analysis, and he told me so in brutal fashion. I then redid those that analysis, sent it back to him, and he found more problems. He's like, okay, this is better, but it still ain't great. And then he sent it back to me, and I redid it. I sent it back to him, or them. I don't know who it was. It's for astronomy, the referee is anonymous. I sent it back. They still didn't like it. And I talked with my collaborators, talked with my advisor. I talked with Dr. Monnier, John, who is basically is the expert in this field. And it was the camera that I was using. And I was like, I don't know what to do with this. I don't know what more I can do. Can you tell me what I can do to make this better? And they're like, no, your referee is being unreasonable. And they spoke to the editor and they were like, listen, we have done the best that we could to appease this referee's concerns. And the referee agrees this is good science. The referee in every review said this is good science. They just had problems with how I was analyzing or interpreting some of those results. And they're like, dude, we're at an impasse. What are you going to do about it? And so the editor was like, all right, we will publish it we will publish the last iteration, and they will tell the editor, listen, cool your jets. We're going to publish it, and this is what's going to happen. And so it got published, finally. And so thank you, Stephanie. I'm glad you're interested. And so that's an example of the review process. That's an example of how the peer review process works. Sometimes it's combative like that. Sometimes it's not. You have basically three, when you submit a paper to a journal, you have three possible outcomes. They can also say, this is fantastic. This is, publish it immediately. Put it in the New York Times. Do not change a thing. This is fantastic. Or they can come and say, I would not wipe my ass with this. This is complete shit. What the fuck are you doing submitting this to a journal? Or they can do somewhere in between, which is the vast majority of what I've seen. I've seen the other two extremes. I had a professor, the dude was amazing. He literally put a paper in, and that was the response. Well, not the New York Times part, but he was like, yeah, this is perfect. Publish it. I've got no substantive notes, grammatical things, but he's like, yeah, publish it. And the grammatical things, I think the editor took into account. And I've had some colleagues who submitted to journals and they're like, no, we are not publishing this. You need to go back to the drawing board and redo this entire experiment, these observations, and then redo it. But what typically in the vast majority of cases is you submit your work, it gets refereed. The referee says, all right, you're onto something here. This is good stuff, but you're making some errors. I don't believe the interpretations that you're making or the analysis that you are doing is questionable. Either they'll believe that it's completely wrong or they believe that you're doing it in error, and they will tell you so. And then you go back and you revise. And then you send it back and they check it over and go. And usually it's a bing, bang, boom, done. You send it in, the reviewer looks at it, makes their comments, sends it back. You deal with those comments, you send it back in. The reviewer says, great, you have done what I've asked, have it published. In other cases, the referee can just have problems that you are not, and you're only communicating through email. So it's not like you can hash it out over the phone call. Because again, you don't know who this person is, and there is a valid discussion to be had as to whether or not that's a good idea. If that is not done in other sciences, from my understanding, astronomy is anonymous with a single referee. I think physics at one point was anonymous with 2 referees. Some other sciences, I think, are just not anonymous at all. So that is a valid discussion to have as to whether or not astronomy needs to move to a different system of referee peer review. And so, da-da-da-da. Oh, you had a paper, Clive? Not surprised. I am very much not surprised. But yes, it is very rare to have a paper go through where a reviewer looks at it and be like, "Oh yeah, I got no problem with this." So, howdy, Floretta. Let's see. There was when Rob upgraded to the B1900 for the telescopes. Yeah, not so much. No, not so much. So yes, the P900 joke was that is a running gag with Clive. I'm surprised he didn't ask if my interferometer needed a container, because I have an answer for that actually, and the answer is no, it doesn't. It probably should to make it less dusty, but this particular interferometer open to the air, so it's easy to work on. Dr. Nimrod, good morning. I'm doing all right. I think I was right in that yesterday I was a bit hypomanic. Today my energy level is lower, but I'm not depressed, anything like that. I have energy. I have motivation to do shit. I have just what I would consider to be normal procrastination of not wanting to do shit. So yeah, I'm doing all right. I really wish I could, interact with people physically, but that's something I always have all over the place. So every school basketball games has 2 referees, and they are not anonymous. They make wrong calls. Stephanie, valid. That is yes. Oop, wrong one. Yeah. I mean, hell, NFL has 5 referees, and they make bad calls all the time. The peer review process is not perfect. And, if we want to continue this analogy, for the vast majority of cases, those mistakes really wouldn't have affected the outcome of the game. In some cases, they do. In some cases, a referee's blown call will affect the outcome of the game. But in my experience with sports, that's very, very rare. And, that's possible. It's possible that a paper will be submitted to a referee, and the referee, it will have a glaring issue, and the referee won't catch it. That gets us to archive, which, again, that is an entirely different discussion. Dr. Wells had mentioned very early in the stream about submitting it to archive. Archive is a repository of papers that are not peer-reviewed, but usually are in the process of peer review. Sometimes people just have a really cool idea that they want to get out there, and so they'll write a paper, put it on archive, and just be like, hey, what do you guys think? Because essentially that's really the goal of, or that's the 2 reasons why archive exists. One, the minor one is that it's free. You don't have to pay the journal to access those articles. But you have to keep in mind they have not been peer reviewed yet. So the final paper that does get published may be different in some manner. So basically allows you to get your ideas out there for free. And the second one is it allows you to get your ideas out there for free because you're in the review process and you want other eyeballs on this other than your referees. So you can say, hey, to friends of yours or obviously you'll send this stuff to your collaborators, but you can send it to people who are friends or I guess you could send it to enemies. Anybody can look at archive essentially, and they can look at it. And if they see a glaring mistake, they'll let you know. You can, your email, where is it? Is my email on here? Well, my contact information is on here. My phone number is on here. My email address should also be on here. For some reason, it is not. I thought it was. But my contact information is on there, so they can find me and find my email fairly easily. So they will. So you put it on archive to basically put it out there into the community to get more eyeballs on it, other than your referee. Now the question comes into play of when exactly, at least for astronomers, when exactly do you put it on archive? What part of the refereeing process is it most appropriate to post to archive? Do you post it before the refereeing process even starts, where you have a raw, it's most raw, and it has not been touched by anyone else's bias? Or do you post it after, where the referee has basically said, okay, this is good to go, and you're simply waiting for the editor to get their act together and actually get it published? Do you push it then when it has been fully reviewed, but just hasn't been published because of time constraints? Or do you post it somewhere in between? I've heard arguments for both sides that seem to be compelling to me. On the one side, if you post it before, then you can potentially, when a referee comes back and say, this is crap and this is why, you can then, someone else can have told you, no, this is pretty good, but watch out, somebody might have a problem with it for these reasons, and you can basically get a second opinion on the reviewer. But the second one, or the reason why you want to do it after the review, is because that process I just talked about may not be so cut and dry. That process, too many cooks in the kitchen. You might get too much information, too many varying viewpoints, and it just confuses the process and slows everything down. So when do you publish to archive? That's up to you. Let's see. Humans are infallible. Yes. Yeah, you're never going to get rid of it. I'm going to buy a P900 to the negative 616 power as soon as I have money. Okay. Didn't know that was a thing. Save your money and get a P100. I'm just going to use my cell phone because it kind of comes with the phone. Too advanced. Yes. So archive, the nice thing about it is that it allows you to communicate results quickly and widely. I can see someone also who isn't even really at the stage where they are sending it to an editor, and they're like, all right, I want to see if I am completely wrong-headed with this. Put it on archive and see if anyone sticks up and says, what the hell is this nonsense? Electroplasmic wake? What the hell is that? Something that would, so you don't basically you don't get a really bad nasty gram from your reviewer. So you can kind of, as a first check, to see whether or not this is actually a valid piece of work or not. So, all right. I think I'm going to wrap this up because I'm getting at 2 hours. And so let me close this down. I am going to end as I started. And I'm going to do the happy bit first. Settings, present, share screen. That one. So I've recently, by Dr. Tapioca Weasel, I have recently been put onto this channel, Maya Atkinson, and I'm pretty sure I'm mispronouncing that. Specifically, her series on Bad Science Sundays. I like it. I like the format. I like the people involved. I highly recommend it. I definitely highly recommend that you check it out. And if you don't absolutely hate it, subscribe. They really want to be able to get this, get her up to 500 subs as soon as possible, so they can get that sweet NASA chill check money. Kidding. So yes. Check out Maya Atkinson. Good stuff. I recommend it. I recommend, and I wholeheartedly recommend it. And I'm curious what you would think about it. So I'm definitely going to keep track of it, because I want to also want to see just how quickly she beats the shit out of me in terms of number of subs that I've got. Because right now I have about 100 more than she does. Well, about 75 more than she does. So we'll see. Anyway, the next thing I want to talk about is a little bit more sobering. As I said at the very beginning, I am concerned about the triggered limey. I haven't looked at Discord, so maybe I have been, there's been news about it. And again, I know I myself hate being checked on. I hate welfare checks. I hate that sort of shit. But I also, on the other hand, understand why people do it. Because, it's scary. It's scary to believe that someone you like, care about, love even, could hurt themselves. So, Limey has been apparently going through some shit. He announced that he was not going to be on YouTube any longer, and that he was giving up a lot of other stuff. I've also heard that he is selling his computer and selling some of his worldly goods. These are not great signs. These are fairly textbook signs of self-destruction. They can be something else. Again, I could be way overblowing this, but they are signs. And so what I would ask is, if you actually watch this, get in touch with us, dude. Just let us know that you're okay. Let us know that what I'm reading in your announcement is not what I'm reading in your announcement. Reach out to somebody, and let us know that you're okay, because you have folks worried. If for those of you don't, what's the word I'm looking for? If you know someone, like right now, he has been difficult to contact, from my understanding. So if you know someone who knows him personally, who can get him on the phone, or better yet, go by his house or go by wherever he's currently at and just, check on him, I would really, really appreciate it. Because as I said, I'm worried about what's going on there. And I know he's, that is all I've got to say on that. So Maya has one up on you, as she has a good size of atheist community she chats with. I did notice that. I did notice a distinctive atheistic bent to the conversations that I've encountered. I would really like to, I hope that doesn't become an obstacle, because I think when atheism becomes anti-theism, then I have problems. When people make statements that seem to completely disregard or disrespect the fact that I believe, I have a hard time getting over that. So we'll see how it goes, and go from there. So, yes. And so now I will play my outro, and yes, it still has not been fixed. So the Patreon page is kind of messed up, but I hope you've enjoyed this. And if you watched all the way through, thank you so much. If you watched just 5 minutes, thank you so much. If you want to help support the channel, particularly the observatory, please consider becoming a Patreon. That link is in the description. And all that money goes to the observatory itself. We recently just purchased a new planetary camera, which I am very excited about using for the public through this upcoming semester and beyond. So with that, peace out, clear skies.